chapter number 12, that's about linear programming. Now this is again totally new concept for us. Linear programming has mainly application in industry, or you can say even in management also, or more precisely even commerce. LP problems has application in these three different areas. Okay, now why LP programming, linear programming? So LP linear programming problems are mainly with these two concepts. One is to maximize the profit, or you can say to minimize the cost minimization, minimize the cost with given resources. This is the main objective of any LP problem. LP problems are mainly to maximize the profit, minimize the cost with given resources. Okay, now here maximization of the profit or the minimization of the cost, this combined things, this one and this one, that is sometimes called optimization. Maximize or minimize, that depends upon the problem. In general, this is called what? In general, optimization of the problem, optimization of the given problem. So in general, here we can say that linear programming is used to optimize the given problem. What we understand by optimize the given problem? Either to maximize profit, that's the objective of any industry problem, and minimize the cost, that is again objective of any industry problem. So it has more or less application in management, or you can say in industry. So this is what the concept of LP problems, optimization. What? Optimization. That means it includes both the things, maximization as well as minimization. This is just at introductory level I have mentioned. You can just read the introduction, you will realize further. Now next, how the LP problem looks. So the next point here is I'll write LP. LP means linear programming problem. LP problem formulation. The general format of LP problem, linear programming problem. We want to write the general format of what? Linear programming problem. So they, with some variables, we have some function which is to be maximize or minimize. So we write, let's take z equals to a function of two variables. I'll write f of x comma y. Right, this is a function of two variables, x and y. Two variables. Let me call these variables as x and y. So this function is called here objective function. Right. If this function is about profit, then we maximize the objective function. If this function is about cost, for example, then we minimize this. So every time there is a question of what? Optimization of such function, and such a function is known as what? Objective function. Now here the maximization or minimization is always under certain resources, that is under certain conditions. So here conditions will be given to you in terms of two variables which are linear inequalities, if you remember. So we'll be having linear inequalities in two variables. Let me state those inequality in general here. So I'll write one linear inequality, a1x b1y plus, let's write c1 in two variables. For example, this is greater than or equal to 0, or it may be less than or equal to 0. Then a2x plus b2y plus c2, it may be greater than or equal to 0 or less than or equal to 0. It may be this or this or this, remember, and so on. You may have number of conditions. So this the above objective function is under this condition. So these are called here, these are called constraints, or the conditions are called linear constraints. These are called linear constraints. That means conditions. Constraints means conditions. And variables x and y are usually non-negative, that is greater than or equal to 0. So this is called a non-negative condition, or non-negative variables. So this is the general format of every linear programming problem. What's the format? This is the format. It has objective function. Normally objective function is always a linear function in our case. So if you want, you can write like this, ax plus by. This is the objective function in general, right? Which is either to be minimized or maximized. That's called optimization. So one is objective function. You have some conditions. This function is to be maximized or minimized under these conditions. These conditions are called constraints here, or linear constraints, with this additional condition that variables are usually non-negative, that is 0 or positive. So these are the parts of any linear programming problem. What are the parts? Mainly objective function and conditions, which are called the constraints. These are the two parts of any LP problem, linear programming problem. What are the parts? I repeat, one is objective function, as I stated here, and the other one, that is, these are constraints or conditions. Now question is how to maximize or minimize this function. This is our main objective. Either you maximize this function or you minimize this function, right? Every time you will be having either maximum value of this function or minimum value of this function, which is called optimization. Okay, now question is how to maximize or minimize this objective function. There are a number of ways. Here in this chapter we use graphical method. We use graphical method to maximize, to find the maximum. I'll write maximum or minimum value of objective function, maximum or minimum value of the objective function under the given conditions of the objective function with given constraints, with given here conditions or constraints. That's what we want to do. We use which method? Graphical method. So it is more or less based on 11 standard linear inequalities you are going to do. Okay, as we were doing, you know how to draw simple straight line functions. So we draw a number of linear inequalities, we find the common region, and then we see how to get the maximum or minimum values. That's what we want to do. So what I'll do, I'll start with a simple example so we can understand instead of going general technique. So I'm taking the first problem, which is about LP problem. So let's see that. So as I told you, here is a simple LP problem. The question is solve the LP problem graphically only. In our syllabus we have graphical method. So what is the question here? Maximize z equals to 4x plus y. You know that this is called which function? Objective function. Objective function either should be maximize or minimize under certain conditions. So subject to these constraints. How many constraints you are given? 2 constraints. X plus y is less than or equal to 50. You know that this is a linear inequality. 3x plus y less than or equal to 90. This is the other linear inequality with this non-negative condition. So we represent this region graphically, and then let's see how to get the maximum value of this function. Fine. So first part is just from 11th standard. We represent these constraints graphically. We represent those constraints. How many constraints are there? There are 2 constraints. What are those? One is nothing but, which one constraint? That is x plus y. X plus y is here less than or equal to 50, and 3x plus y less than or equal to 90. So here constraints graphically and get a feasible ration. Feasible ration means what? Common ration. You know, such things we were doing even in 11th standard. Here this is just a new word. Feasible means common ration, common of all these linear inequalities. Once I do it, you will realize. Okay, so for this let's consider 2 coordinate axes here. You see we are concentrating where? In the first quadrant only because of this. So I'm just showing in the first quadrant. Such things we were doing even in 11th standard. This is the x-axis, this is y-axis. Why we are concentrating at first quadrant? Because you are already given that x and y both are greater than or equal to 0. Now I need till 50 and 90. So I'll just write 10, 20, 30, 40, 50, 60 and so on. Here also I'll write same way, 10, 20, 30, 40, 50, then 60 and so on till 90. You can write it. Okay. Now first we are presenting this. You know how to draw this straight line. Put x equals to 0, y will be 50. So 0, 50. Where is 0, 50? 0, 50 is here, you know. 0 then 50. Now I'll put y equals to 0. So x will be 50. So over here, right? Such things, this is simply a straight line. Remember, this is not great thing now for you being 12th standard students. So here this is 50, 0. So I'll draw an equality. So here, you know, there is a line through these 2 points, which is this one. Fine. Okay, this is equation of which line? X plus y equals to 50. Now which region? This region or this region? Recall 11th standard. So what we do? Normally we take origin. What about origin? Is this 0, 0 satisfy this equation? Yes. 0 plus 0 is less than or equal to 50. So the required region is this. I'll just put 2, 3 dots. We are interested in common region. Okay, so this region, not this. In the first quadrant. Why in the first quadrant? You know here, x greater than or equal to 0, y greater than or equal to 0. Fine. Now we are drawing the second inequality. So put x equals to 0, y will be 90. 0 then 90. Suppose 70, 80, 90 here, roughly. I'm just showing roughly here. Here I have 90. Put y equals to 0, then x will be 30. So 30 somewhere here. Now I'll draw a line through these 2 points, straight line through these 2 points. So let me draw it. So this is a straight line through those 2 points. This is the equation of which line? You know, 3x plus y equals to 90, remember. Because of this inequality, either you have this side region or this side region. Okay. Now put 0, 0 here. 0 plus 0 less than or equal to 90. Again this side region. This triangle region, this black line says lower region. So I suppose you must have realized there is a common region. Right? Such things we did number of times in 11th standard. This is a common region. Common means what? All the points from this satisfy both the inequalities. Why we are concentrating at the first quadrant only? Because of these two conditions. So this is the regions. 0, if I call this as O, A, I'll call this as B, I'll call this as C. O, A, B, C. This is the region. So that's O, A, B and C. This is feasible region. Feasible region means what? Solution region. Feasible means common or possible or feasible region. So solution must be within this region only. Now there is a theory, we are not getting into that. We just get these corner points. This is always a polygon. You see 1, 2, 3, 4 sides here. This is a polygon. We just find the coordinates of these points, vertices. These are called corner points. Right? So we find corner points. These are all new words for you. Corner points means what? Vertices. One is this, the other one is this, one more is this, and one more is this. Some of them are obvious. What are the coordinates of the corner point O, which is 0? 0, that is origin. So I'll write here. So one is here O, which is 0, 0. Even coordinates of A also you can write very easily. You just recall it is on the x-axis and this is 30. So what are the coordinates of A, which is 30, 0. Coordinates of C also you can write very easily. How do we write it? That is here on the y-axis, x coordinate is 0. So this is 0, 50. Now how do we get the coordinates of B? You can see that it is the intersection of these two lines. So we solve these two equations. So we'll get the coordinates of B. So for B, solving given two equations. Solving equations, which two equations? X plus y equals to 50 and 3x plus y equals to 90. How will solve? By elimination method, as we were doing. So just put the minus sign, this will get cancelled. This is minus 2x and this is nothing but how much? Minus 40. So x equals to 20. Put x equals to 20 in one of these two, so we'll get the y equals to 30. So therefore, what about the coordinates of B? 20, 30. So you now got the all corner points B, C, A and O. Almost you are very close to the solution. Once you get the corner points, we prepare such table like this. So here corner point and value of function, value of the function which we called z here. Fine. Now which is first point? 0, 0. Put into the function. Where is the function? Here. 4x plus y. 0 plus 0. So this will be 0. The next point, let's write 30, 0. I'll put into the function. 30, 0. Which function? Let me write here. Function is given by 4x plus y. So I'm putting here. X equals to how much I'm putting? 30. So it will be 120 here plus zeros. The next point, that is 20, 30. So x is 20, y is 30. So this is 80 plus 30. So 110. The next point is 0, 50. These are corner points, remember. If I put this much, you will get just 50. Okay. Now there's a theorem that says that function attains maximum or minimum value at corner points. So where the function has maximum value? Over here. This is the maximum value of the function. Maximum value. of the function, at which corner point it attains the maximum value at 30, 0. And that's all in all about the solution. You can just write, if you want, in form of table here. This is a tabular form. So function attains the maximum value equals to 120, and that's what you need to do. So I'll write the final line. Therefore, maximum value of objective function z is 120. Fine? Not difficult, remember. What we did? I repeat the entire solution. You are given this LP problem, which consisting of objective function and these conditions, which are called constraints. This we represented graphically as we were doing in 11th standard. We got the common ration. This is a common ration. You know how to do this. Keep on finding the common ration. This is a common ration. It will be always a polygon. So these are the corner points. This is sometimes, we'll come to that later on, this is sometimes called bounded ration, remember. This is called bounded ration. We have some questions there, the region may be unbounded like this. We'll see, but here this is called the bounded ration. So it has corner points, this and this. These are the corner points. We get the coordinates of the corner points 0, 0, 30, 0. How we got the coordinates? By solving these two equations. Coordinates of C 0, 50. Fine. Once we get the coordinates points, we prepare this table and just look at where the function attains the maximum value. Here it is a maximum value 120. So the maximum value of the objective function is 120 with the given conditions. That's what you have to do in every question. That's all in all about this chapter, remember. This much only, very simple chapter. See one more question. Minimize the objective function z equals to minus 3x plus 4y subject to 1x plus 2y less than or equal to 8, 3x plus 2y less than or equal to 12. These are the two constraints. This is objective function and this is non-negative condition. So your solution region must be where? In the first quadrant. So we concentrated first quadrant. So represent this inequality graphically. Represent inequalities graphically and get the common ration. Get the common means here feasible. Feasible means solution ration. Feasible ration. Feasible means common of these two, as we did in 11th or even in previous examples. So I'll just represent two coordinate axes now. Now in constraints we have smaller values. So I'll take here 1, 2, 3, 4, 5, 6. This is up to you, remember. Based on the given inequalities, you can choose these units. All these things you know. Here this y-axis, this is x-axis. Now we represent the first one. I'm sure you must be knowing how to represent this. How to represent this? Put x equals to 0. So what is y? 2y equals to 8. So y is 4. So 0 then 4. This point. 0 then 4. You need at least 2 points to represent this line. Now I'll put y equals to 0. So x will be 8. So this is 7. This is 8. Here y is 0, remember. So y is 0, then 8, 0. So we have this line. I'll show this line. That passes through these 2 points. Okay. Now question is this region or this region, because this is inequality. So what we do, normally we take origin. What are the coordinates of origin? 0, 0. Check whether it satisfies this inequality or not. 0 plus 0 less than or equal to 8. So this lower region. here you can just put 1 or 2 dots, lower region. Fine. I hope this is clear to you. Let me repeat this. How to decide the region, whether this is this region or this region. For that, what you need to do, put 0, 0 here. Why we are choosing 0, 0? Because it's easy to check. You can take any point, but normally we were doing same thing in 11th standard also. We are putting 0, 0. 0 plus 0 less than or equal to 8. That means the region which is origin side, that is this side. So this is your required solution for this inequality. What's the equation of this inequality? That is x plus 2y here equals to 8. Fine. Now we go to the second one. There, let's put x equals to 0. So what is y? 2y equals to 12. 2y equals to 12. So y is 6. This point. 0, then 6. Let's put y equals to 0. If I put y equals to 0, then 3x equals to 12. So it will be x equals to 12 by 3, which is 4. So 4, 0, this point. So this will be the line here. This is the line. That is 3x plus 2y equals to 12. Fine. Now again, question is this region or this region. So what we do? We choose origin. Put 0, 0 here. 0 plus 0 less than or equal to 12. So it will satisfy 0, 0. So the region, that is origin side. So this region. And it is in the first quadrant, remember. So for second line it is this region. For first line it is this region. So which is common? This much. This is a common region. This polygon. This is a common region. Common region means what? Feasible region. Feasible region means what? Every point from this region satisfies both the inequalities. That's called feasible region. What are the corner points? One is origin. The other one A, which is 40, 0. I'll call this as B, which we don't know. How do we get the coordinates of B? By solving these two equations. And one more is C. That also you know, 0, 4. Fine. Here it is 4, 0. Here it is 0, 4. This we need to get. So we find corner points now. We find corner points. What are the corner points? Vertices of the polygon. So one is origin, that's obvious. Here 0, 0. The other one is A, that's quite obvious here. You can see it is 4. So 4, 0 on the x-axis. B we need to find. What about C? C, you know here 1, 2, 3, 4. This is 4. So this is 0, 4. And now, like previous question, we get the B. How do we get the B? It's intersection of these two lines. So we solve these two lines by elimination method. So for B, I'll write for B, solving these two equations. Solving x plus 2y equals to 8 and 3x plus 2y equals to 12. So let's put the minus sign here. So this will get cancelled. So I'll get the minus 2x equals to how much? Minus 4 here. So x is 2. If x is 2, put in any one of these two equations. Therefore y equals to, if I put 2 here, then 8 minus 2, 6. So y is 3. So the coordinates of the corner points B will be 2, 3. So now you got all corner points. So I'll prepare the table. I'll write here corner point here and function z. Function z equals to, you have which function here? Just recall the function, minus 3x plus 4y. Fine. Let me write the corner points now. What are the corner points here? One is origin 0, 0. The other one is A, which is 4, 0. The next one is B, which is 0, 4. No, B is, 2, 3 here. 2, 3. And C is 0, 4. Now we put where in the function. So I'm putting in the function 0, 0. So this is 0. 4, 0 I'm putting. Minus 12 plus 0. So this is minus 12. 2, 3. Minus 6. If I put 2, x equals to 2. This is minus 6. If I put 3 here, 12. So this will be 6. 0, 4. So this is 16. Now you just go back to question. You are asked to minimize this. So here this is the minimum value. Minimum is minus 12. Where minus 12? At 4, 0. So I'll write finally, therefore minimum value of z is minus 12 at which place? At 4, 0. That's all in all about solution. I repeat, what we do usually in LP problems, we represent these inequalities. These are called constraints here graphically. We find the common region. Up to this we were doing in 11th standard. Then we get the coordinates of these corner points. Here again you have bounded region, remember. You have bounded region. If you have unbounded region, what is to be done? I will discuss. But right now we have bounded region. So for bounded region, you have these corner points which are actually vertices. 0, 0, this one, and this one. So we can write this directly 0, 0, 4, 0. How we got this? By solving this two equation, and this is 0, 4. And then just we have prepared this table here. Which table? The table showing the value of the function at the corner points. So here at the corner points, the minimum, you are asked to minimize, remember, minimum value of the function. So which one is minimum? Minus 12. Where it obtains? At this corner point 4, 0. Clear? Let's do one more example. Here objective function is this, which is to be minimized under this function. Minus 50x plus 20y, subject to these three constraints. Solution is in which quadrant? First quadrant. This is non-negative condition. You have three conditions. Now if you cannot draw directly these three inequalities, you can show like these also. Let me show you. So first inequality, 2x minus y equals to, you can write minus 5, and you can prepare the table like this. We used to do such things in 11th standard. Second inequality, 3x plus y, I'm writing equals to 3, here x and y. Third inequality, here 2x minus 3y equals to 12, x and y. Okay, now x and y normally we select 0, so it becomes easy. If I take x is 0, what is y? 5. Next, if I take y equals to 0 here, y is 0, so what is x? Minus 5 by 2, that is minus 2.5. It can be any point, remember, not necessarily always you should choose 0, but I have chosen here. So this is a tabular form. I hope this one is clear to you. If I take x is 0, y will be 5. Y is 0, 2.5, that is x. Now here, come to this. X is 0, y will be 3. Y is 0, x will be 3x 1. Just look at there. This is one more table for this. X is 0, y, here y will be 3. Y will be 3. And if y is 0, 3x equals to 3, so x is 1. And over here, one more, let's put x equals to 0, so y will be minus 4. Put x equals to 0, minus 3y equals to 12, so y will be minus 4. If y is 0, then x will be 6. Now we represent 0, 5, this, so we'll get this line, we represent this, you will get this line, and similarly this. So we are presenting this one in the Cartesian plane, and then we try to find the common region. Let's see. So first x0, y5, 0, then 5 here, then minus 2.5, then 0, minus 2.5 on the x-axis, then 0 somewhere here. So this is a line, this is the first line. Like this, we will have a line like this. We are interested in first quadrant, so like this. This is not important, but line would be like this. It passes through this. This is which line? Here it would be 2x minus y equals to minus 5. Okay, what about second line? 0, then 3, 0, then 3, 0, then 3 here. Okay, and 1, then 0. Where is 1, then 0? Here, over here. So second line will be this. Second line will be this one. Okay, now what is equation of this line? 3x plus y equals to 3. Okay, before I draw the third one, let me see where is the common ration here. See, for first line, either it is this ration or this ration. So I'm trying for this origin. I'm putting 0, 0 in the inequality. 0 minus 0. 0 is greater than or equal to minus 5. Is this true? Yes. Putting 0, 0 here. 0, 0. 0 is greater than or equal to minus 5. Is this true? Yes. So where is 0, 0? In this part. So region will be this. I'm just putting a dot here. This is a required region, not this region. Are you getting me? This line divides into two parts. One is this part and the other one is this part. I'm saying I have chosen 0, 0. It satisfies the first inequality. Therefore, the region that contains 0, this region. But we are not interested in this. We are interested in first quadrant. So this is our region. Bounded by this line, this much, remember. So right now I'll just put one dot because we want the common. Okay. What about the second line? Whether it is this region or this region. This region or this region. So I'll check for 0, 0. Fine. Or let me check for this, for example. 0, 0. 0 plus 0 greater than or equal to 3. Is this true? No. 0 plus 0 greater than or equal to 3 is not possible. That means this is not the required region, this side region. So either this side or this side. Up to this we are restricted to this. This is not the region in the solution. Why? I repeat. I have chosen this point 0, 0. Is this 0, 0 satisfy this inequality? No. 0 plus 0 greater than or equal to 3. Is this possible? No. That means this is not the required region. This side region is the required region. Fine. I hope you are clear with this. This is purely from 11th standard. So up to this is the region in the first quadrant. This much. Bounded by this line, then this, not this one, remember, then this right hand side region. Okay. Now we draw the third line. Where is third line? 0, then minus 4. And 6, 0. 0, then minus 4 somewhere here. I'll not show that, somewhere here on the negative y-axis. And 6, 0. Where is 6, 0? Somewhere here, roughly. 6, 0. So that line will be like this. This is the line. Okay, this is equation of which line? Let me write here. It is nothing but 2x minus 3y equals to 12. Now either region will be this or this. So check whether origin satisfy or not. So what about 0, 0? 0 minus 0 less than or equal to 12. Yes, it satisfies. That means the region containing 0, 0, that is this region. But we want in the first quadrant only, remember. So this portion. So finally, these two lines were saying this region. this line saying this region. So this is your region. Remember, this is your feasible region, this one. And you can see that it is unbounded. It's not finite region. It's not a polygon. This is unbounded region, right? It is endless. It goes on. Every point from this shaded region, you pick up any point, whether I take this point, it will satisfy all the three inequalities. That's what we understand by the solution region. So this is our solution region. This is called unbounded region here. In previous two examples, you were having solution region as a polygon, which was bounded. Here it is unbounded. Okay, but still we have corner points. What are the corner points here? One is this. The second one is this one. Third one is this. And fourth one is this. These are the four corner points. Let me label this as, for example, I'll start from here. A, B, C and D. You can write coordinates of all these four corner points very easily. Clear? I hope this much is clear to you, right? Corner points are important, otherwise your solution will be wrong, remember. A, B, C and D. This is unbounded region. So feasible region is unbounded. Feasible region is unbounded with corner points. With corner points. Corner points here you can write very easily. The one I'll start with A, which is 6, 0. You can just see in the graph. The other one B, which is nothing but you can write again very easily, which is 1, 0. The next one is C, which you can write very easily, 0, 3, and D, that is 0, 5. You have drawn the rough graph. Rough does not mean wrong, remember. आपको इतना भी रफ ड्रॉ नहीं करना है कि आपको पता ही ना चले. See, I've drawn in such a way that from the points you can write coordinates very easily. 6, 0, then 6, 0, 1, 0, 0, 3 and 0, 5. Rough does not mean that you draw the wrong graph. Keep in your mind. Otherwise, to get the coordinates of the corner points becomes difficult for you. Fine. Now we prepare the table as we were doing. So corner point and function here. Function z equals to minus 50x plus 20y. Okay. So here 6, 0, 1, 0. Labeling is not important. ABC and 0, 5. I'll put into the function. We put 1 by 1 in the function. So 6, 0 if you put, it will be here how much? Minus 300. Then 1, 0, it will be minus 50. Then 0, 3, 0, 3, so it will be 60, and 0, 5, it will be 100. Fine. So this is the tabular for the given function. Okay. Now after doing this, we need to do something extra because region is unbounded here. You are asked to minimize the function. Now this is the minimum value, you know, minus 300. Now what extra we need to do is, we draw now, this you need to do always whenever you have unbounded region. Draw the line. Which line? That is minus objective function, remember. Where is objective function? You know, minus 50x plus 20y is less than minus 300. Why we took this less than? Because you are asked to minimum. If you are asked the maximum, then we would have taken greater than. I'll come to that later on. Let me come to this. If you are asked for minimum the objective function, you see, you are asked to minimize the objective function. So we draw this line. Which line? Minus 50x plus 20y. This is objective function. Less than minus 300. Then at least before you draw, you can divide by how much? 10. So you will get the 5x plus 2y less than minus 30, just dividing by 10. Now we draw this. So I'm drawing this line. Which line? Minus 5x plus 2y less than 30. From where I wrote this? This is objective function. Objective function less than minimum value. Right? There is a theory behind this why like this, but whenever you have unbounded region, always you need to draw this extra line after doing this. So you draw which line? Objective function less than minimum value, which is minus 300, and then just dividing by 10. Now I'm drawing this line here again. So if x is 0, what about y? X is 0, then y is minus 10. 0, then minus 10. I'm showing that. So it is somewhere here. Somewhere here. 0, then minus 10. Somewhere here. Okay. I hope this is clear to you. 0, then minus 10. If y is 0, what about x? If y is 0, then x will be 6. So you have 6 comma 0. 6 comma 0 is again here. 6 comma 0 is somewhere here. So I will have the line like this. See, I cannot draw here, but 6 comma 0, so somewhere like this. This is the line. Always we put the dotted line. This is which line? I'll show it. Minus 5x plus 2y equals to minus 30. Now theory says that whether you take this feasible region or this region, is there any common points between these two? That the region determined by this line and feasible region? If yes, then, so see what I've written. The half plane means this, whether it is this or this. Half plane obtained by this line. This is the line. Whether it is this half plane or this half plane has a common points with the feasible region. It has common points. You can see this. If it is this half plane, then these all are the common points. If it is this half plane, these are the all common points. So whether it is this half plane or this half plane, that half plane has a common points with the feasible region. Therefore, the conclusion is the function has no minimum value.